Today's notes are on determinants. Now, a determinant, kind of a new idea for us, and kind of a strange procedure to find a determinant. So, if you see this notation, this is saying here that matrix A equals, okay, this just stands for some numbers. Now, if you ever see something like this, it looks like the absolute value of matrix A. Now, it's impossible to find the absolute value of a matrix. That's just something that's not defined. So if you see those vertical bars, that means the determinant of matrix A. So keep in mind, determinant is noted by these vertical bars. Or we could say, let's put them around this entire matrix. Well, to find the determinant of a 2 by 2 matrix, what we do is we multiply diagonally in this direction. Then we subtract what we get when we multiply diagonally in this direction. Now, it's kind of a strange process, and to be honest with you, a determinant on its own really doesn't have a whole lot of mathematical value. What does it mean? Really, on its own, it doesn't mean a whole lot. However, we can use determinants to do a number of different things that we're going to get into in the next set of notes. So today we're going to practice just finding a determinant, which on its own it doesn't tell us a whole lot. The next set of notes are going to get into what they're used for, what they're good for. Okay, so let's just practice finding some determinants. So directions here say find the determinant of matrix A. Okay, we know to find a determinant we need to multiply diagonally this way, and then subtract what we get when we multiply diagonally this way. So 8 times 2 is 16, minus negative 5 times 3 is negative 15. Now right there's the biggest mistake people make, just subtracting negatives. Just be real careful with that. 16 minus what we get this way, negative 15. So the determinant is 31. And your determinant in general will just be a numerical answer. Alright, that's not bad. Let's get a more complex example. Let's say we need to find the determinant of this matrix. Well, there's a method that works only for 3 by 3 matrices where we can look at the diagonals once again. Now, the strange thing is, if we look at the first diagonal, we're probably okay, 5, 1, and 6. But if we look at the next diagonal, we just have that 2 and 8, and then there's a 3. So what do we do with that? Well, for 3 by 3 matrices, here's something we can do. Take that first column and write it down again, 5, 7, and 4. Take the second column, write it down again, 2, 1, and 9. And what this will allow us to do is look at each of these diagonals and multiply each of these. So just like before, we want to multiply along these diagonals. So let's see what we get here. 5 times 1 times 6 is 30. Plus 2 times 8 times 4 is 32. Plus, wait a minute, it's not 32. What am I talking about? It's 64. Plus 3 times 7 times 9, which is 189. Now, you might say, why are you adding all of these? In the previous problem, we subtracted. We added and subtracted. Well, in this one, all the diagonals that go upper left to lower right, we're going to add. Then we also have diagonals that go lower left to upper right, and we're going to subtract those. So in a sense, it's the same as the last problem. We add diagonals that go in one direction, subtract that go in another direction. So now I'm going to say let's subtract 4 times 1 times 3, well that's 12, minus 9 times 8 times 5, that's 360, minus, that's a 6 in there, 6 times 7 times 2, that's 84. So if we add and subtract all these, we get a value of 173, which is the determinant of matrix A. Now this method here only works for 3 by 3 matrices. So if you get a bigger matrix, you cannot use this adding the column method or any other matrices, but it works for 3 by 3 matrices. Let's talk about another method that actually works for all matrices. So we're asked to find the determinant of this matrix A. So here's what we do for that. We want to think of this 3 as just a separate element, and from that 3 I'm just going to cross off everything in the same row and in the same column. Here's what we want to find. We want to know what 3 times determinant of what's left is. -5, 4, 1, and 6. All right, I can do the same thing again by either following across that top row or down that first column. I'm going to go down the first column. You'll see why in just a bit. So I'm going to circle this 0, cross off everything in the same row, same column, and then I'm going to say -0. Why am I saying minus? Well, remember when we found determinants the first time, we added some diagonals, subtracted others? Here we're going to go plus, minus, add some of these numbers times determinants, subtract every other one. So -0 times this determinant. 8, -7, 1, and 6. Then, let's get this out of here. We need to do that one last time. I'm going to circle this 8 here. I'm going to cross off what's in the same row and column. And I'm going to say plus 8 times this determinant. 8, -7, -5, and 4. Now this method here works for any square matrix. So if I have like a 5 by 5 matrix, I could do this. Also with this method, we could either go across the top row, go down the first column. There's other ways we can go too, but let's not confuse ourselves. So either of those directions is fine. I chose to go down the first column simply because we have this 0 here. Let's think about this. Whatever this determinant is, we're multiplying it by 0, right? So this entire term in the middle is going to be 0. Hey, that saves me some time. So if you see zeros in your matrix, use them. Okay, so let's see here. This is going to give us 3 times -5 times 6 is -30, -4, -34. Then -0 times all this, I'm not even going to write that down because I know it's equal to 0, plus 8 times 4 is 32, -35, that gives me -3. So the value of this determinant, if we multiply here, 3 times -34, that gives me negative, what is that? -102, plus, this gives me -24. So this entire value, if I add this together, is -126. So the determinant of this original matrix is -126. So I could have done that by putting more columns in. I can also do that by using this new method here, using the rows and columns. Either method will give me this answer. Okay, let's find one last determinant, and then we'll get a little practice with this. Oh my goodness, this doesn't look good. Now, warning for you. Adding columns and doing the diagonal method will not work here. That method only works for 3 by 3 matrices. So to do this, we're going to have to say 2 times this determinant, -8 times another determinant, plus -7 times a determinant, -4 times this determinant. This is going to get messy. All right, there's got to be an easier way to do this. All right, let's pull out our graphing calculator. You kind of knew this was coming, that, okay, there must be an easier method. So let's put that matrix in, and I've got it already in there in place of matrix A. So in matrix A, I have typed all of this in here. So I'm going to quit editing my matrix. I'm going to go back to the matrix menu, and if I go to the math menu, look at the very first choice, DET, that stands for the determinant. If I hit enter, it brings that command to the home screen. Then I need to tell the calculator what matrix I want to find the determinant of. So I'm going to get the name of matrix A. And if I hit enter, it gives me that numerical value. If I would have tried to do that by hand, I probably would have made a mistake somewhere along the line. Letting my calculator do it, just make sure I typed in the numbers correctly and finds that determinant. Now we could have used that method for the previous few problems, but we should probably practice doing some of those by hand. But if you get more complex matrices like this one, I would encourage you, use your calculator as a tool to find this determinant. Okay, so like I said, the determinant by itself doesn't tell us a whole lot, but our next set of notes is going to get into what determinants are useful for, and we can use them for a lot of different applications.